The universe is a vast, mysterious place filled with riddles that even the brightest minds can't solve. Picture this: a force so powerful it's pulling entire galaxies toward it, yet we can't see it. A star that dims and brightens in ways that defy all logic. Signals from deep space that arrive in bursts, then disappear without a trace. These aren't scenes from science fiction, they're real cosmic puzzles happening right now, all around us. Today, we're diving into 30 of the most baffling, awe-inspiring mysteries the cosmos has to offer. Phenomena so strange they challenge everything we think we know about space, time, and reality itself. From invisible matter shaping the universe to objects behaving in ways physics can't explain, these enigmas keep scientists up at night. And by the end of this journey, you'll understand why the universe is far weirder and far more wonderful than we ever imagined. So buckle up, we're about to explore the greatest unsolved secrets of the cosmos. Now, let's unravel the first and perhaps most famous cosmic mystery: dark matter. Imagine looking up at the night sky, seeing stars and galaxies glittering in the darkness. But here's the twist: what you're seeing is only a tiny fraction of what's actually out there. Scientists estimate that dark matter makes up roughly 27% of the universe, yet it's completely invisible. It doesn't emit, absorb, or reflect light, which means even our most powerful telescopes can't see it directly. So how do we know it exists? Because its gravitational pull is impossible to ignore. Galaxies spin so fast that, according to the laws of physics as we know them, they should fling themselves apart. But they don't. Something unseen is holding them together, acting like cosmic glue. That something is dark matter, its gravity weaving an invisible scaffold that shapes the entire universe. Without it, galaxies as we know them wouldn't exist. But despite its overwhelming presence, dark matter remains elusive. It doesn't interact with ordinary matter in any way we can easily detect, which makes hunting it down one of science's biggest challenges. So, how are scientists trying to solve this mystery? One approach is smashing particles together at incredible speeds in machines like the Large Hadron Collider, hoping to create dark matter particles in the debris. Another method involves ultra-sensitive detectors buried deep underground, shielded from cosmic interference, waiting for the rare moment a dark matter particle might bump into an atom. Then there's the study of cosmic phenomena, like the bending of light around galaxies, a telltale sign of dark matter's gravitational influence. Yet, after decades of searching, we still haven't directly observed it. Some theories suggest dark matter might be made of entirely new kinds of particles, ones that don't fit into our current understanding of physics. Others propose that our laws of gravity might need revising altogether. Whatever the answer, cracking this cosmic puzzle could revolutionize our understanding of the universe. And here's the wildest part: dark matter isn't even the strangest thing out there. That title might belong to its even more mysterious counterpart, dark energy, which we'll explore next. But for now, one thing is clear: the universe is far more than what meets the eye, and dark matter is the ghostly hand shaping everything we see and don't see from the shadows. But if dark matter seems mysterious, wait until you hear about its even more enigmatic counterpart, dark energy. Just when we thought we'd uncovered the universe's biggest secrets, it throws us another curveball. Imagine the cosmos as a balloon slowly inflating, with galaxies drifting farther apart. Now, picture that balloon suddenly starting to blow up faster and faster, defying all expectations. That's the bizarre reality we're facing. Dark energy, making up a staggering 68% of the universe, is the mysterious force behind this accelerating expansion. Scientists first stumbled onto this puzzle in the late 1990s while studying distant supernova. They expected to find the universe's expansion slowing down due to gravity's pull, but instead it was speeding up. It was like tossing a ball in the air only to watch it shoot into space. This discovery flipped cosmology on its head. earning researchers the Nobel Prize and leaving the rest of us grappling with a cosmic riddle. So what is dark energy? The truth is we don't fully know. The leading candidate is Einstein's cosmological constant, a sort of background energy woven into space itself. But here's the catch: when we calculate how strong this energy should be, theoretical predictions are off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, the biggest mismatch in science. Some theorists argue dark energy might not be constant at all. Enter quintessence, a dynamic field that changes over time, potentially growing stronger or weaker. Others propose even wilder ideas, like extra dimensions leaking gravity into our universe or flaws in Einstein's relativity. But while the explanations vary, one thing's certain: dark energy is winning its tug of war with gravity, pushing galaxies apart so relentlessly that distant corners of the cosmos will one day disappear beyond our view forever. What does this mean for the universe's fate? If dark energy keeps dominating, we could face a big rip, where not just galaxies but atoms themselves are torn apart. Or space might stretch into a cold, empty void, stars fading into isolation. Yet despite its apocalyptic implications, dark energy also offers a humbling reminder: we've barely scratched the surface of cosmic understanding. And just beyond this mystery lies another, a colossal gravitational anomaly pulling entire galaxies toward it, hidden behind our own Milky Way. But that's a story for next time. But before we dive into the next cosmic puzzle, let's take a moment to appreciate just how strange the universe can be. If dark energy wasn't enough to boggle the mind, there's something even more unsettling lurking in the depths of space. Something so massive it's tugging at entire galaxies like a cosmic puppeteer. Hidden behind the thick veil of stars and dust in our own Milky Way lies a gravitational enigma known as the Great Attractor, and it's pulling us toward it at a staggering 2 million kilometers per hour. Picture this: every galaxy in our local cosmic neighborhood, including our own, is being drawn toward a single point in space like leaves caught in a river's current. The problem: we can't see what's pulling us. The Great Attractor sits in the direction of the constellation Centaurus, but it's obscured by the Milky Way's zone of avoidance, a region so dense with gas, dust, and stars that optical telescopes struggle to see through it. It's like trying to spot a lighthouse through a thunderstorm. So how do we study something we can't even see? Enter infrared astronomy. Unlike visible light, infrared wavelengths can pierce through cosmic dust, allowing telescopes like NASA Spitzer and the European Space Agency's Herschel to map what lies behind the Milky Way's glare. What they've found is astonishing. The Great Attractor isn't just one massive object but a colossal supercluster of galaxies, with a gravitational pull so immense it distorts the very fabric of space around it. But here's where it gets even weirder. The Great Attractor itself seems to be moving, pulled by something even larger, a mind-bending structure called the Shapley supercluster, nearly 800 million light-years away. It's as if we're caught in a cosmic tug-of-war, with our local galaxies caught between these two giants. What does this mean for us? While the Great Attractor won't swallow the Milky Way, our galaxy's motion is mostly sideways relative to it. Its existence forces us to rethink the universe's large-scale structure. Why are galaxies clustering in such strange, lopsided ways? Could there be even greater gravitational anomalies lurking in the unseen reaches of space? For now, the answers remain as elusive as the attractor itself, a shadowy reminder that even in our own cosmic backyard, the universe still holds secrets we're only beginning to uncover. And just when you think space couldn't get any stranger, wait until you hear about the next mystery: bursts of radio energy so powerful they outshine entire galaxies in milliseconds. But that's a story for another moment. Now let's turn our attention to something that flashes across the cosmos in the blink of an eye, but leaves scientists utterly baffled: fast radio bursts, or FRB. Imagine a burst of radio waves so powerful it releases more energy in a millisecond than our sun does in 3 days, yet it vanishes without a trace before we can even pinpoint its origin. These cosmic flashes are among the most enigmatic signals in the universe, and they're coming from galaxies billions of light-years away. The first FRB was discovered in 2007, buried in old radio telescope data, and since then we've detected hundreds more. Some explode once and disappear forever like cosmic fireworks. Others, like the infamous FRB 1211-2, repeat in unpredictable patterns, taunting astronomers with clues they can't quite decipher. What's causing these extreme bursts? The theories range from the exotic to the downright speculative. One leading candidate is Magnetar's neutron stars with magnetic fields so intense they could strip the information off a credit card from halfway across the solar system. When these stellar corpses experience starquakes or magnetic flare-ups, they might unleash the colossal energy we detect as FRBs. In 2020, astronomers even caught a magnetar in our own galaxy firing off an FRB-like signal, adding weight to this idea. But not all FRBs fit this mold, leaving room for other possibilities. Then there's the elephant in the room. Could some FRBs be artificial? The idea that advanced civilizations might be behind these signals isn't just science fiction. The repeating patterns of FRB 1211-2, for instance, cycle every 157 days like clockwork, sparking debates about engineered broadcasts. While most scientists lean toward natural explanations, the sheer strangeness of FRBs keeps the door open for wilder hypotheses. Here's what makes FRBs especially tricky: they're incredibly hard to study. Lasting just milliseconds, these bursts require ultra-sensitive telescopes and perfect timing. Facilities like the Canadian Chime Array scan the sky around the clock, catching dozens of FRBs and mapping their origins to distant galaxies. Each new detection peels back another layer of the mystery, revealing that some FRBs are accompanied by X-rays or even visible light hints that could crack the case wide open. What's clear is that FRBs aren't just cosmic oddities. They could be probes into the universe's most extreme environments, helping us map the invisible matter between galaxies or test Einstein's theories in ways we never imagined. And every time we think we've got them figured out, they surprise us again. Whether they're the death cries of magnetars, messages from afar, or something entirely new, one thing's certain: the universe loves keeping us guessing. Speaking of cosmic surprises, our next mystery takes us from fleeting radio bursts to a star that dims in ways nobody can explain. But that's a story for another moment. Now let's shift our gaze to a star that's been playing a cosmic game of hide and seek with astronomers. Meet Tabby's star, officially known as KIC 8462852, a seemingly ordinary star in the constellation Cygnus that behaves like anything but. What makes it so bizarre? Its light doesn't just flicker. It plunges by as much as 20% at times, as if something massive is passing in front of it. And no, it's not a planet. Even a Jupiter-sized world would only block about 1% of its light. So what's casting this colossal shadow? The theories range from the plausible to the downright sci-fi. When astronomer Tabetha Boyajian and her team first spotted these strange dimming patterns in data from the Kepler Space Telescope in 2015, the internet exploded with speculation. Could it be alien megastructures like a Dyson swarm, a hypothetical array of solar collectors built by an advanced civilization to harness the star's energy? It's a tantalizing idea, but before we jump to extraterrestrials, let's look at the natural explanations. One leading theory points to vast clouds of dust orbiting the star. Unlike the orderly rings around Saturn, this dust could be clumpy and uneven, occasionally blotting out huge chunks of light. Observations from the Hubble and Spitzer telescopes detected more dimming in ultraviolet than infrared, which fits the dust scenario. Small particles scatter shorter wavelengths better. But here's the catch: the dust would need replenishing, as it should dissipate over time. So where's it coming from? Some suggest a shattered moon or a catastrophic collision between planets, leaving debris in its wake. Then there's the star's long-term dimming. Over the past century, Tabby's star has faded by an astonishing 14%, something no other known star does naturally. Could it be surrounded by a giant, uneven dust cloud from a recent planetary collision? Or is something else at play, like internal stellar processes we don't yet understand? Recent studies have tilted the scales toward natural explanations, but the mystery isn't solved. In 2021, the Lick Observatory caught the star dimming again, and citizen scientists worldwide scrambled to observe it. Each new dip adds data, but also new questions. Why do some dips last days while others stretch for weeks? Why is the dimming so irregular? Even the dust theory struggles to explain every anomaly. What's fascinating is how Tabby's star challenges our assumptions. Most stars behave predictably, but this one refuses to follow the rules. Whether it's cosmic dust, planetary wreckage, or who knows, something even stranger, it's a reminder that the universe still has tricks up its sleeve. And as we keep watching, one thing's certain: this star isn't done surprising us yet. Up next, we'll tackle a question that haunts every search for cosmic mysteries. If the universe is teeming with life, why does it feel so empty? That's the heart of the Fermi Paradox, and it's waiting just ahead. Now let's turn our attention to one of the most perplexing questions in all of science. Why, in a universe so unimaginably vast, does it feel like we're utterly alone? This is the Fermi Paradox, a puzzle that strikes at the heart of our search for cosmic company. The numbers seem to scream that we shouldn't be the only ones here. Our galaxy alone has hundreds of billions of stars, many with planets in the habitable zone. Even if life is rare, the sheer scale of the universe suggests civilizations should have arisen countless times. So where is everybody? The paradox takes its name from physicist Enrico Fermi, who famously asked, "Where are they?" during a casual lunch conversation in 1950. His point was simple: if advanced civilizations exist, they've had billions of years to spread across the galaxy. We should see signs of them: radio signals, megastructures, probes. Yet our telescopes and detectors hear only silence. This contradiction between expectation and reality has spawned dozens of theories, each more mind-bending than the last. One of the most unsettling explanations is the Great Filter. This idea suggests that somewhere along the path from simple life to interstellar civilization, there's a nearly insurmountable barrier, a filter, that wipes out almost everyone. The terrifying question is whether we've already passed it or if it still lies ahead. If it's behind us, say, the leap from single cell to complex life is extraordinarily rare, then we might be among the universe's lucky few. But if the filter is ahead, like self-destruction through nuclear war or AI, our future could be bleak. Then there's the zoo hypothesis, which paints a more serene picture. Imagine Earth as a cosmic nature preserve, with advanced civilizations deliberately avoiding contact to let us develop naturally. It's an elegant idea, but raises questions. Why no leaks, no accidental signals? And who enforces this galactic prime directive? Others propose that space is simply too big. Even if civilizations exist, the distances and timescales might make communication impossible. Imagine two ants on opposite sides of the planet trying to find each other. Some theories get even wilder. Maybe advanced beings have transcended physical form, uploading their minds into virtual realities and abandoning the outer universe. Or perhaps we're looking for the wrong signs. What if they communicate via neutrino beams or dark matter? There's even the chilling possibility that civilizations tend to self-destruct once they reach a certain technological level, leaving the cosmos littered with silent ruins. The truth is, we don't know, but the Fermi Paradox isn't just about aliens. It holds a mirror to humanity. Are we destined to vanish like so many might have before us, or will we break the mold? Every search for extraterrestrial intelligence, every scan of the skies, is really a search for our own future. And until we find answers, the universe's silence remains its most haunting mystery. Coming up, we'll rewind to a moment when that silence was briefly broken, a single, enigmatic radio signal that still sparks debate decades later. The WOW signal is next, and its story is as strange as they come. But amidst the eerie silence of the cosmos, there was one fleeting moment that made astronomers sit up and take notice. In the summer of 1977, the Big Ear radio telescope in Ohio picked up something extraordinary. A 72-second burst of radio waves so intense that astronomer Jerry Amon scrawled, "Wow," in red ink next to the data. Decades later, the WOW signal remains one of the most tantalizing mysteries in the search for extraterrestrial intelligence. The signal came from the direction of the constellation Sagittarius, near a star group called Chi Sagittarii. What set it apart wasn't just its strength, 30 times louder than cosmic background noise, but its frequency. It hit precisely 1,420 MHz, a quiet band where natural cosmic noise is minimal, and hydrogen, the universe's most abundant element, emits energy. It was as if someone had picked the perfect cosmic radio channel to shout, "We're here." Yet just as suddenly as it appeared, the signal vanished. Despite dozens of follow-up scans, including recent efforts by the Allen Telescope Array, it never repeated. This one-off nature fuels the debate. Was it a message from an alien civilization, or something mundane we still don't understand? Skeptics suggest it could have been a reflected signal from human-made space debris, or an undiscovered celestial phenomenon. But none of these explanations fully fit. The frequency wasn't used by satellites at the time, and no known natural process emits such a narrow, powerful burst. Then there's the tantalizing possibility that it was alien. If a civilization aimed a focused transmission at Earth, whether a deliberate beacon or an accidental leak from a communications system, this might be exactly what we'd detect. The fact that it lasted 72 seconds aligns with the Big Ear's scan time, as if the telescope caught the tail end of a drifting signal. Some researchers even speculate that the signal's intensity hints at an origin much farther away than Sagittarius, perhaps amplified by a gravitational lens, a natural cosmic magnifying glass. But here's the twist: if it was aliens, why haven't we heard anything since? The WOW signal's brief appearance might suggest that interstellar communication is rare, fleeting, or deliberately sparse. Or perhaps civilizations send signals only periodically, and we just happen to be listening at the right moment. What's undeniable is how the WOW signal captured imaginations. It's a reminder that in the vast quiet of space, even a single blip can rewrite our questions. Up next, we'll dive into a phenomenon where particles defy the rules of classical physics, entangled across cosmic distances in ways Einstein called spooky. Quantum entanglement is waiting, and its implications are as profound as they are strange. Now let's turn our attention from mysterious signals to something even more mind-bending, a phenomenon so bizarre that even Einstein struggled with it. Picture two particles, perhaps photons or electrons, born from the same event. They fly apart, separated by thousands of light years, yet somehow they remain mysteriously linked. Change one and the other instantly responds, no matter the distance. This is quantum entanglement, and it defies everything classical physics taught us about how the universe should work. Einstein famously called this spooky action at a distance, and for good reason. In our everyday world, if you toss a pair of dice, what happens to one doesn't affect the other. But entangled particles ignore this logic. Measure one, and its partner's properties snap into place instantly, faster than the speed of light. This isn't just theoretical. Experiments have confirmed it time and again, shattering our intuition about space and time. One of the most groundbreaking tests happened in space itself. In 2017, China's Misha satellite shattered records by beaming entangled photon pairs to ground stations over 700 miles apart. Even at that staggering distance, the particles stayed eerily in sync. When researchers changed the polarization of one photon, its partner matched it perfectly, as if they were still side by side. This wasn't just a lab curiosity, it proved entanglement survives the harshness of space, opening doors to unimaginable technologies. But how? How can particles communicate faster than light, seemingly breaking relativity's golden rule? The truth is, they aren't communicating at all. Instead, quantum mechanics suggests these particles exist in a shared state, a kind of cosmic unity until measured. It's as if the universe keeps them in sync behind the scenes, beyond our classical understanding. Some physicists speculate this hints at deeper layers of reality, where space and time aren't the rigid frameworks we assume. The implications are staggering. If we can harness entanglement, we might one day build unhackable quantum networks or computers solving problems in seconds that would take regular machines millennia. Even wilder theories suggest entanglement could be woven into the fabric of spacetime itself, a hidden thread connecting the cosmos. Yet for all its promise, entanglement remains deeply puzzling. Why does the universe allow such connections? Are there limits to how far this spookiness stretches? One thing's certain: quantum entanglement forces us to rethink reality's foundations. And as we push experiments further into deeper space, across greater distances, we may uncover truths even stranger than fiction. Up next, we'll confront another cosmic head-scratcher: what happens to the information swallowed by black holes? It's a paradox that pits quantum theory against gravity, and the answer might reshape physics forever. Now, shifting our cosmic gaze from the eerie connections of quantum entanglement, we arrive at one of the most heated debates in modern physics, a puzzle so profound it threatens the very foundations of our understanding. Imagine tossing a book into a blazing fire. The pages burn, the ink vanishes, but in theory, if you could somehow collect every ash particle and trace the smoke's path, you might reconstruct the book's contents. But what if you threw that book into a black hole? According to Stephen Hawking's groundbreaking work, not even a trace would remain. This is the black hole information paradox, and it pits two pillars of physics, quantum mechanics and general relativity, against each other in a battle with universe-shaking stakes. Here's the problem: quantum mechanics insists that information can never truly be destroyed. It might get scrambled, hidden, or transformed, but it's always preserved in some form. Yet black holes, as described by Einstein's general relativity, are cosmic vacuum cleaners. Once matter crosses their event horizons, it's gone forever, crushed into a singularity of infinite density. Hawking turned this idea on its head in the 1970s when he calculated that black holes aren't entirely black. They slowly leak energy, now called Hawking radiation, and over eons they evaporate entirely. But here's the catch: Hawking's math suggested this radiation carries no information about what fell in. Poof, everything, every star, planet, or hapless astronaut vanishes without a record, violating quantum law. The physics community split into warring camps. One side, led by Hawking himself for decades, argued that information truly is lost and quantum mechanics must be rewritten. The other side, including luminaries like Leonard Susskind, insisted the universe wouldn't allow such cosmic amnesia. They proposed wild solutions like holographic theory, where all information swallowed by a black hole is encoded on its two-dimensional surface like a cosmic DVD. Others speculated that black holes might not evaporate completely but leave behind microscopic remnants packed with hidden data. Then, in 2016, Hawking dropped a bombshell. Collaborating with colleagues, he proposed that information might escape via soft hair, subtle quantum imprints on a black hole's event horizon. Though unproven, the idea reignited hope for a solution. Meanwhile, cutting-edge experiments with lab-grown analog black holes using sound waves or light aim to simulate Hawking radiation's behavior. Early results hint that information might indeed survive, scrambled but intact. Why does this matter? Beyond theoretical sparring, the answer could redefine reality. If information is preserved, it suggests a deeper, hidden order to the cosmos, a universe where even the most destructive forces obey quantum rules. If lost, we'd need a radical new physics, one where the past isn't just hard to see, but fundamentally erased. As telescopes like the Event Horizon Telescope peer deeper into black holes' hearts, and quantum computers simulate their mysteries, we may soon witness a revolution, one proving that even the darkest corners of space can't keep secrets forever. Next, we'll unravel a cosmic coincidence so strange it seems almost intentional, an alignment in the universe's oldest light that shouldn't exist. Is it a flaw in our models or a clue to something far grander? Now, let's turn our attention to a cosmic oddity so peculiar it's been dubbed the Axis of Evil, a name that sounds like it's straight out of a sci-fi thriller, but in reality, it's a genuine mystery that's keeping cosmologists up at night. Picture the universe's oldest light, the cosmic microwave background, or CMB for short. This faint glow is the afterglow of the Big Bang, a snapshot of the infant universe frozen in time. Scientists have studied it meticulously, expecting it to be uniformly random, a cosmic fingerprint with no preferred direction. But here's where things get weird. The fluctuations in this ancient light aren't as chaotic as they should be. Instead, they appear to align bizarrely with the plane of our solar system, as if the universe is subtly tipping its hat to us. This discovery throws a wrench into one of cosmology's bedrock principles, the cosmological principle, which states that the universe should look roughly the same in all directions on large scales. No special place, no favored axis, yet the CMB's alignment with our local cosmic neighborhood suggests a violation of this rule. It's like rolling a dice thousands of times and always getting a 6 when the dice is tilted a certain way. Statistically, it shouldn't happen, and yet it does. When researchers first spotted this anomaly in data from the Wilkinson Microwave Anisotropy Probe, or WMAP, in the early 2000s, skepticism ran high. Maybe it was a fluke, an artifact of measurement errors or galactic interference. But then the Planck satellite, with even sharper precision, confirmed the signal. The so-called axis isn't just a minor quirk. It's a large-scale pattern stretching across billions of light-years, with fluctuations in the CMB's temperature appearing to know about the orientation of our solar system. Theories abound, but none have delivered a knockout answer. Some propose that the anomaly is a ghostly imprint of something beyond our universe, a shadow cast by a neighboring cosmos in a hypothetical multiverse. Others wonder if it's evidence of exotic physics, like a primordial magnetic field that twisted space-time in the universe's earliest moments. Then there's the unsettling possibility that we're seeing a statistical illusion, a cosmic selection bias where we're mistaking local patterns for universal truths. After all, if you stare at any dataset long enough, you might find phantom patterns, but the stakes are high. If the axis is real, it could mean our understanding of the universe's birth is missing a critical chapter. What makes this even more tantalizing is that the axis isn't just a one-off oddity. It seems to connect to other cosmic anomalies like the mysterious dark flow, where clusters of galaxies appear to stream in a preferred direction. Could these puzzles be pieces of a larger, unseen picture? For now, the axis of evil remains a thorn in the side of cosmology, a reminder that the universe still holds cards close to its chest. Next, we'll examine a baffling glitch in the motions of our farthest spacecraft, an unexpected slowdown that had scientists scrambling for answers before uncovering a surprisingly humble explanation. Now, let's shift our gaze from the vast mysteries of the cosmos to something closer to home. Well, relatively speaking. In the late 20th century, humanity's farthest robotic explorers, the Pioneer 10 and 11 spacecraft, began behaving in a way that left scientists utterly perplexed. These intrepid probes, launched in the early 1970s to study the outer planets, had long completed their primary missions and were drifting toward interstellar space when something strange happened. They started slowing down, not just any slowdown, mind you. This was an unaccountable deceleration, a tiny but persistent tug backward, as if some invisible hand was gently pressing the brakes. The effect was subtle, about 300 billionths of a meter per second squared, but over decades and billions of miles, it added up to a deviation that couldn't be ignored. For years, this pioneer anomaly became a thorn in the side of physicists, a glitch that seemed to defy Newton's laws of motion. Was it evidence of new physics? A flaw in our understanding of gravity, or something even weirder? Theories flew fast and furious. Some speculated that dark matter might be clumping near the solar system's edge, exerting extra gravitational drag. Others wondered if Einstein's theory of general relativity needed tweaking at extreme distances. More exotic ideas even floated the possibility of higher dimensions subtly influencing the probe's trajectories. The anomaly became a darling of fringe science, with some claiming it as proof of undiscovered forces or even, yes, alien interference. But as is often the case in science, the truth turned out to be far more mundane, though no less fascinating. After decades of head-scratching, researchers finally cracked the case. The culprit: heat. Not some cosmic force, but the gentle, uneven glow of the probe's own radioactive power sources. As the plutonium in their generators decayed, it emitted heat which radiated outward in all directions. But here's the catch: the spacecraft's design meant slightly more heat escaped from the rear than the front. This tiny imbalance created a minuscule but constant thrust, a photon recoil effect that acted like a soft brake. Once this thermal radiation was meticulously modeled, the anomaly vanished. The universe wasn't breaking the rules after all. We'd just missed a detail in the fine print. Yet the pioneer anomaly's legacy endures. It's a reminder of how even the smallest overlooked factors can lead to big mysteries, and how science, when patient and rigorous, can untangle them. It also underscores a humbling truth. Sometimes the universe's greatest puzzles aren't cosmic in scale, but hiding in plain sight, waiting for us to look closer. Next, we'll turn to an interstellar visitor that defied classification, a bizarre object that streaked through our solar system, leaving astronomers debating whether it was a comet, an asteroid, or something entirely unexpected. Now, let's journey from the mysteries within our solar system to an enigma that arrived from far beyond it. In 2017, astronomers spotted something extraordinary, a visitor from interstellar space, the first ever confirmed. They named it Oumuamua, Hawaiian for scout or messenger from afar arriving first. And from the moment it was detected, this peculiar object defied every expectation. At first glance, Oumuamua appeared to be a rocky asteroid, a relic from another star system. But the more scientists observed it, the weirder it became. For one, its shape was unlike anything in our solar system, a bizarre, elongated sliver, estimated to be up to 10 times longer than it was wide. Imagine a cosmic cigar tumbling through space, or perhaps, as some daringly suggested, a flattened pancake. Then came the real head-scratcher. Oumuamua wasn't just coasting passively under gravity's pull. It was accelerating as if pushed by an unseen force. This acceleration sent theorists into overdrive. Comets often speed up due to outgassing sunlight vaporizing their ices, creating a propulsive jet. But Oumuamua showed no visible coma or tail, the usual hallmarks of outgassing. Could it be an exotic, dark comet, venting hydrogen or other invisible gases? Or was something else at work? The lack of clear outgassing led to even wilder speculation, including the controversial suggestion that Oumuamua might be artificial, a solar sail or probe from an advanced civilization. The possibility, though slim, couldn't be entirely dismissed. After all, its unusual shape and acceleration fit some theoretical designs for lightweight interstellar probes. But Occam's razor favors natural explanations, and most scientists lean toward Oumuamua being a fragment of a Pluto-like world, rich in nitrogen ice that vaporized silently in sunlight. Others propose it was shorn from a planet by a cosmic collision, sent hurtling into the void. What makes Oumuamua truly tantalizing is that we may never know for sure. By the time it was spotted, it was already racing away, too faint and distant for further study. It left behind a trail of questions. How many more interstellar interlopers slip through our solar system unseen? Are they all this strange? Oumuamua's fleeting visit reminds us that the cosmos is full of surprises, and some mysteries slip through our fingers just as we begin to grasp them. Next, we'll confront a puzzle closer to home, one that challenges our very understanding of the universe's building blocks, the missing baryon problem. Turning our gaze from interstellar visitors to the very fabric of the cosmos, we encounter a puzzle that strikes at the heart of what the universe is made of. You'd think we'd have a pretty good handle on ordinary matter, the stuff that makes up stars, planets, and even us. But here's the catch: when astronomers tally up all the visible matter in the universe, it only accounts for about half of what theoretical models predict should be there. This glaring discrepancy is known as the missing baryon problem, and it's one of the most persistent head-scratchers in modern cosmology. Baryons are the heavy particles, protons and neutrons, that form the building blocks of atoms. According to the standard model of cosmology, baryons should make up roughly 5% of the universe's total mass and energy. Yet, when we count up all the luminous matter in galaxies, gas clouds, and other visible structures, we're coming up short. So where's the rest of it? The answer might lie in the vast, shadowy filaments of the cosmic web. Picture the universe as an enormous network of threads, with galaxies clustered at the intersections like glittering beads. These threads or filaments are made of diffuse gas so hot it's invisible to optical telescopes. This gas isn't just sitting there. It's a turbulent, superheated plasma with temperatures reaching millions of degrees. The challenge: detecting it requires looking beyond visible light. Enter X-ray observatories like Chandra and advanced radio telescopes, which have begun spotting faint traces of this elusive material in the spaces between galaxies. One leading theory suggests that these filaments contain the missing baryons, woven into a sparse but massive reservoir of warm, hot intergalactic medium, or WIM. Simulations show that over half of the universe's ordinary matter could be hiding in this form, a cosmic sleight of hand that's kept it just out of sight. But confirming this isn't easy. The WIM signal is incredibly faint, and mapping its distribution is like trying to trace the outline of a ghost. Another possibility is that some baryons are tied up in hard-to-detect forms, like rogue planets or faint, starless galaxies. Or perhaps our understanding of the early universe's baryon budget needs tweaking. Either way, solving this mystery isn't just about filling a ledger, it's about testing the foundations of cosmology itself. Every missing baryon is a clue, a piece of the puzzle that could reshape how we see the universe's structure and evolution. As we peel back the layers of this enigma, we're reminded that even the most familiar things, like the matter that makes up our world, can hold secrets we're only beginning to uncover. Next, we'll delve into another cosmic oddity, one that's much closer to home but no less baffling: the Moon's ancient magnetic field and how it vanished without a trace. Now, let's turn our attention from the hidden matter weaving through the cosmos to a mystery much closer to home, our own Moon. It might surprise you to learn that the Moon wasn't always the magnetically quiet place it is today. Billions of years ago, it once boasted a magnetic field powerful enough to rival Earth's. But today, that field has all but disappeared, leaving scientists puzzled over how it vanished and what clues its absence might hold about our celestial neighbor's turbulent past. The Moon's magnetic field is thought to have been generated by a dynamo effect, much like Earth's. This process involves the movement of molten metal in a planetary core, swirling like a cosmic engine to produce a magnetic shield. For Earth, this dynamo is still churning, fueled by the heat left over from our planet's formation and the radioactive decay of elements deep within. But the Moon, smaller and less massive, should have cooled far too quickly to sustain such activity for long. So how did it manage to maintain a strong magnetic field for hundreds of millions of years? One leading theory points to a dramatic early chapter in the Moon's history. Shortly after its formation, the Moon may have been much closer to Earth, subjected to intense gravitational forces that stretched and squeezed its interior. This tidal heating could have kept the Moon's core molten far longer than expected, powering a dynamo strong enough to generate a magnetic field. Supporting this idea, lunar rocks brought back by the Apollo missions bear traces of magnetism, suggesting they solidified in the presence of a robust field. But then something changed. Around 1 billion years ago, the field began to fade, likely as the Moon's core cooled and its dynamo sputtered out. Without this protective shield, the Moon's surface was left exposed to the relentless bombardment of solar wind and cosmic radiation, a stark contrast to Earth, where our magnetic field still deflects these harmful particles. Another twist in the story comes from recent studies of lunar samples, which hint that the Moon's magnetic field might have flickered on and off in its youth. Some researchers propose that massive asteroid impacts could have temporarily reignited the dynamo by stirring up the Moon's core, like a spoon swirling in a cup of hot liquid. If true, this would mean the Moon's magnetic history was far more dynamic than we ever imagined. Understanding why the Moon's magnetic field vanished isn't just about solving a lunar puzzle. It's a window into how small rocky worlds evolve over time. It also raises tantalizing questions. Could other moons or even exoplanets have experienced similar magnetic births and deaths? And what does this tell us about the potential for life on distant worlds, where magnetic fields play a crucial role in shielding atmospheres? As we piece together the Moon's magnetic past, we're reminded that even the most familiar objects in the night sky still guard secrets waiting to be uncovered. Next, we'll journey to the outer reaches of the solar system, where another geometric marvel defies explanation: the strange and persistent hexagon swirling over Saturn's north pole. Leaving behind the mysteries of our Moon, we now cast our gaze toward the ringed giant Saturn, where an even more bewildering spectacle awaits. High above its north pole, a colossal, perfectly shaped hexagon has persisted for decades, defying every expectation of how weather behaves in our solar system. This six-sided storm, large enough to fit 4 Earths side by side, is unlike anything seen on any other planet, and it continues to baffle scientists with its unnatural precision and endurance. First spotted by the Voyager missions in the early 1980s, the hexagon was later studied in stunning detail by the Cassini spacecraft. Unlike chaotic hurricane-like storms on other planets, this structure maintains razor-sharp edges and an almost mechanical symmetry, rotating in sync with Saturn's internal rotation rate. What could possibly create such a geometric jet stream in a realm where fluids and gases normally swirl in turbulent, unpredictable patterns? One leading theory suggests the hexagon is a standing wave pattern, a sort of atmospheric echo generated deep within Saturn's interior. Just as vibrations create symmetrical patterns on a vibrating plate of sand, oscillations in Saturn's turbulent atmosphere might carve out this six-sided shape. Laboratory experiments on Earth have shown that rotating fluids can produce polygonal shapes under certain conditions, adding weight to this idea. Yet, no model has perfectly replicated the hexagon's stability or why it locks into 6 sides instead of another number. Another puzzle is the storm's longevity. While most planetary weather systems evolve or dissipate over time, Saturn's hexagon has remained virtually unchanged for at least 40 years. This suggests it's anchored by something far more stable than ordinary atmospheric currents, perhaps tied to Saturn's deep-seated rotation or hidden internal dynamics. Some researchers speculate that the hexagon could be influenced by the planet's layered wind systems, where alternating bands of eastward and westward jets collide to form this bizarre geometric boundary. Adding to the intrigue, the hexagon isn't just a flat shape. It towers high into Saturn's stratosphere, with multiple layers of clouds and gases churning within its walls. Infrared observations reveal that the structure extends hundreds of kilometers upward, creating a towering honeycomb of weather patterns. At its center lies a swirling vortex, a massive hurricane-like storm that could hold clues to the hexagon's formation. The deeper we probe, the stranger the hexagon becomes. Unlike Earth's hurricanes, which derive energy from warm ocean waters, Saturn's storm has no liquid surface to feed it. Instead, it may draw power from internal heat rising through Saturn's gaseous layers. But how this energy translates into such a crisp geometric form remains anyone's guess. This isn't just a curiosity, it's a window into planetary physics. If we can crack the hexagon's code, we might unlock secrets about fluid dynamics, atmospheric behavior, and even how giant planets evolve over time. Could similar geometric storms exist on exoplanets, or is Saturn's hexagon a cosmic fluke, a rare alignment of conditions we've yet to see elsewhere? As we marvel at this celestial enigma, we're reminded that nature often defies our simplest assumptions. Up next, we'll witness another act of cosmic violence, the relentless galactic cannibalism of Andromeda, as it tears apart smaller galaxies in its path. Now we turn our attention from the geometric wonders of Saturn to something far more violent unfolding in our cosmic neighborhood. The Andromeda Galaxy, our closest galactic neighbor, isn't just drifting peacefully through space, it's devouring smaller galaxies in a relentless act of cosmic consumption. This process, known as galactic cannibalism, is reshaping our understanding of how galaxies grow and evolve over billions of years. Recent observations reveal that Andromeda's halo, a vast, diffuse region surrounding the galaxy, is littered with the shredded remnants of smaller galaxies it has absorbed. These stellar corpses, stretched into long streams of stars and gas, are like cosmic breadcrumbs tracing Andromeda's destructive path. One victim, a dwarf galaxy called M32, was nearly torn apart, leaving behind a dense, compact core that now orbits Andromeda like a ghost of its former self. Another, the Triangulum Galaxy, shows signs of being stripped of its outer stars as it spirals toward an eventual merger. What makes this even more fascinating is the sheer scale of time involved. Galactic cannibalism isn't a quick process, it unfolds over eons. Andromeda's gravitational pull slowly disrupts smaller galaxies, stretching them into ribbons before eventually assimilating their stars into its own structure. This isn't just random chaos, it's a key mechanism for how large galaxies like Andromeda bulk up over time. But here's where things get personal for us. Andromeda isn't just feeding on distant, anonymous galaxies, it's on a collision course with our own Milky Way. In roughly 4 billion years, the two galaxies will begin a slow, gravitational dance that will ultimately result in a merger. While the term collision might conjure images of catastrophic crashes, the reality is far less dramatic. The vast distances between stars mean actual stellar collisions are unlikely. Instead, the two galaxies will weave through each other, their gravity distorting their shapes and triggering bursts of new star formation before finally settling into a single, larger galaxy. This future merger raises intriguing questions. Will the Milky Way's spiral arms be torn apart? Could our solar system be flung into intergalactic space? While the chances of our sun being ejected are slim, the night sky will change dramatically as the two galaxies merge, filling with new stars and glowing gas clouds. Studying Andromeda's current feeding habits gives us a preview of what's to come. By analyzing its halo of galactic debris, astronomers can piece together how these colossal mergers unfold and what they mean for the fate of galaxies like our own. It's a reminder that even on cosmic scales, nothing stays the same forever. Up next, we'll venture into one of the universe's most unsettling voids, a region so empty it challenges our understanding of cosmic structure itself. Now let's shift our gaze from the crowded chaos of galactic mergers to one of the universe's most baffling absences, the Boötes void. Imagine a region of space so empty that if the Milky Way sat at its center, we'd have no idea other galaxies even existed until the 1960s. This cosmic emptiness, spanning an almost unimaginable 330 million light-years, is so vast it could fit several thousand galaxies, yet it contains barely 60. That's like finding a desert the size of a continent with only a handful of scattered pebbles. What makes the Boötes void so unsettling is how starkly it defies our expectations. The universe on large scales is supposed to be roughly uniform, like a sponge with evenly distributed holes. But this void is a gaping hole in that cosmic sponge, challenging the cosmological principle that matter should be spread evenly when viewed at grand scales. Some scientists argue it's just a statistical fluke, an improbable but natural variation in the cosmic web. Others whisper about more exotic explanations. Could it be the imprint of an ancient collision with a parallel universe, or the footprint of a super-advanced civilization that somehow cleared the space? While these ideas veer into speculation, they highlight just how perplexing this emptiness is. The few galaxies that do reside in the Boötes void are oddballs themselves. They're isolated, starved of neighbors, and often strangely rich in gas like lone survivors in a wasteland. One theory suggests these galaxies might be failed systems, ones that never fully formed because the void's lack of density left them without the gravitational tug needed to grow. Another eerie detail: the void isn't perfectly spherical. Its irregular shape hints that it might not be a single void but a chain of smaller voids linked together, like cosmic bubbles merging into one gigantic emptiness. But here's the real kicker: the Boötes void isn't alone. Smaller voids exist throughout the universe, but none match its staggering scale. If voids this size are possible, does that mean our understanding of cosmic structure is incomplete? Or worse, could there be even larger voids lurking undetected, hidden by the limits of our telescopes? This isn't just academic curiosity. Voids play a crucial role in the cosmos. They're the yin to galaxies' yang, their emptiness shaping the paths of matter and the large-scale flow of the universe. Studying the Boötes void forces us to confront whether we've underestimated the universe's capacity for weirdness. Up next, we'll unravel the cosmic web itself, the invisible scaffolding that holds the universe together and dictates where galaxies call home. Now, let's weave our way into the grand architecture of the cosmos, the cosmic web. Picture the universe not as a random scattering of galaxies, but as an intricate tapestry, with galaxies strung along vast, invisible threads like pearls on a necklace. These threads, stretching hundreds of millions of light-years, form a sprawling network of filaments, connecting dense galaxy clusters and surrounding enormous voids like the Boötes void we just explored. But how does this cosmic spiderweb hold everything together, and why do galaxies prefer these invisible highways? The cosmic web is the scaffolding of the universe, built from the faint gravitational imprint of dark matter. Though invisible, dark matter's pull shapes the distribution of everything we see. In the early universe, tiny fluctuations in density, like ripples in a pond, grew over billions of years, with gravity amplifying them into the filaments and nodes we observe today. Ordinary matter, the stuff of stars and planets, simply followed these dark matter blueprints, pooling along the densest threads. The result: a universe organized into a web-like structure, with galaxies clustering at the intersections like cities at the crossroads of ancient trade routes. But here's where it gets even stranger. The cosmic web isn't just a static map, it's dynamic. Gas flows along these filaments, funneling into galaxies and fueling star formation. In fact, some of the universe's brightest objects, like quasars, are thought to sit at the web's nodes, gorging on this incoming material. Yet despite its grandeur, the cosmic web is fiendishly difficult to study. Most of it is made up of diffuse gas, too faint to detect directly. Scientists have had to get creative, using the light from distant quasars as cosmic flashlights to illuminate the web's hidden strands, revealing its structure in silhouette. One of the biggest puzzles is why galaxies align so precisely with these filaments. Some theories suggest the web's gravitational tides spin galaxies into alignment, like leaves caught in a river's current. Others propose that the web's structure influences how galaxies grow, with those along filaments merging more often, growing larger and brighter. But the web might also hold clues to the missing baryon problem, the mystery of why we can't account for all the ordinary matter predicted by theory. Could these faint, hard-to-see filaments be hiding the universe's lost atoms? The cosmic web reminds us that the universe is far more connected than it appears. What looks like chaos from a distance is up close an ordered network, a reminder that even in the vastness of space, nothing exists in isolation. And as we peer deeper, we're left wondering, if dark matter's invisible hand crafted this web, what other cosmic designs are waiting to be uncovered? Next, we'll tackle a mystery closer to home, the Hubble tension, a disagreement over how fast the universe is expanding, and why it's forcing scientists to rethink the rules of cosmology. Now, let's turn our attention to a cosmic disagreement that's shaking the foundations of modern cosmology, the Hubble tension. Imagine measuring the speed of a car with two different tools, only to get wildly different results every time. That's exactly what's happening with the universe's expansion rate, and astronomers are scratching their heads over why their numbers just won't match up. The Hubble tension revolves around a single, deceptively simple question: how fast is the universe expanding? To answer this, scientists rely on two main methods. The first involves studying the cosmic microwave background, the faint afterglow of the Big Bang, using space telescopes like Planck. This method calculates the expansion rate, called the Hubble constant, by analyzing tiny temperature fluctuations in this ancient light. The second method focuses on nearby celestial objects like pulsating stars called Cepheids and explosive supernovae, which act as cosmic yardsticks. By measuring their brightness and distances, astronomers can estimate how quickly space itself is stretching. Here's the problem: the two methods should agree, but they don't. The cosmic microwave background suggests an expansion rate of around 67 kilometers per second per megaparsec, while measurements of nearby stars and galaxies peg it closer to 73. That gap might seem small, but in cosmology, even a tiny discrepancy can signal a massive misunderstanding. If both methods are correct, then our current model of the universe, the lambda cold dark matter framework, might be missing a crucial piece. So, what's causing the tension? One possibility is that dark energy, the mysterious force accelerating the universe's expansion, isn't as constant as we thought. Maybe it's growing stronger over time, throwing off our measurements. Another theory suggests the existence of unknown subatomic particles like sterile neutrinos, which could subtly alter the universe's early evolution. There's even a wilder idea. What if our universe isn't uniformly expanding, and we're sitting in a local bubble where space stretches faster than elsewhere? The stakes couldn't be higher. If new physics is needed to explain the Hubble tension, it could rewrite our understanding of everything from the Big Bang to the fate of the cosmos. Already, telescopes like the James Webb Space Telescope are diving into the mystery, scrutinizing Cepheid stars and distant supernovae with unprecedented precision. Meanwhile, upcoming projects like the Vera C. Rubin Observatory aim to map millions of galaxies, hunting for clues in the large-scale structure of the universe. What makes this cosmic puzzle so thrilling is its potential to reveal something entirely unexpected. Whether it's an unseen ingredient in the universe's recipe or a flaw in our fundamental assumptions, the Hubble tension reminds us that even our best models are just sketches of a far grander reality. And as we gather more data, one thing is certain: the universe still has plenty of surprises up its sleeve. Next, we'll venture into the quantum realm, where particles defy the rules of classical physics in one of the universe's most mind-bending phenomena, the Unruh effect. Now, let's shift our gaze to the quantum realm, where reality itself seems to bend under extreme conditions. Picture this: you're floating in empty space, utterly alone in what seems like a perfect vacuum. But what if we told you that if you started accelerating, this seemingly empty void would suddenly come alive with particles? This is the bizarre heart of the Unruh effect, a quantum quirk that blurs the line between motion and reality. The Unruh effect, named after physicist William Unruh, reveals that an accelerating observer would detect particles Unruh radiation, where an inertial observer sees none. Think of it like this: in everyday life, we take for granted that a vacuum is truly empty. But quantum mechanics paints a far stranger picture. According to quantum field theory, what we call empty space is actually a seething sea of virtual particles that constantly pop in and out of existence. Normally, these particles cancel each other out so quickly we never notice them. But when you accelerate, something extraordinary happens. Your motion disturbs this quantum soup, making some of these virtual particles appear real to you. Here's where it gets wild. The faster you accelerate, the more particles you detect, and the hotter this phantom radiation would feel. For example, an observer accelerating at 1g, Earth's gravity, would perceive space as being at a frigid 4/trillionth of a degree above absolute zero. But near a black hole's event horizon, where acceleration becomes extreme due to immense gravity, this effect could theoretically produce a bath of detectable particles. This is why the Unruh effect isn't just a quantum curiosity. It has profound ties to Hawking radiation, the process by which black holes slowly evaporate over cosmic timescales. The implications ripple through modern physics. Some theorists suggest the Unruh effect could help bridge quantum mechanics and Einstein's general relativity by showing how acceleration and gravity might be fundamentally linked. Others wonder if it could explain why different observers might disagree about whether a particle exists, a concept that echoes through quantum paradoxes like the famous Schrödinger's cat. Yet despite its theoretical elegance, detecting Unruh radiation remains one of physics' greatest challenges. The effect is unimaginably weak under normal conditions, requiring accelerations far beyond what current technology can achieve. Some experimentalists are exploring clever workarounds, like using ultra-cold atoms or superconducting circuits to mimic extreme acceleration in controlled lab settings. What makes the Unruh effect so captivating is how it forces us to question our most basic assumptions about reality. Is a vacuum truly empty, or does its nature depend entirely on how you're moving through it? As we push the boundaries of quantum experiments, this phenomenon reminds us that the universe still holds mysteries that defy both intuition and classical physics. Next, we'll journey to the frozen edges of our solar system, where a sudden drop-off in space rocks hints at an unseen cosmic disruptor, the Kuiper Cliff. Now, let's venture into the frozen outskirts of our solar system, where an eerie cosmic boundary lies in wait. Beyond the orbit of Neptune, where sunlight is just a dim speck in the sky, the Kuiper belt stretches out like a vast repository of icy leftovers from our solar system's birth. But something strange happens when we reach about 50 astronomical units from the Sun, the Kuiper Cliff. Here, the number of detectable objects doesn't just dwindle. It practically vanishes. Why is this so puzzling? Well, for decades, astronomers expected the Kuiper belt to gradually thin out the farther you go. Instead, it's as if someone drew a sharp line in space, cutting off the population of icy bodies almost completely. This abrupt edge has left scientists scratching their heads, sparking theories that range from the dramatic to the downright mind-bending. One leading explanation involves an unseen, massive planet lurking even farther out in the darkness. Dubbed Planet 9 by some researchers, this hypothetical world could be 10 times the mass of Earth, orbiting hundreds of astronomical units from the Sun. Its gravitational pull might have shepherded Kuiper belt objects into clustered orbits, or even flung them out of the solar system entirely, leaving behind this stark drop-off. While no direct observations of Planet 9 have been made yet, the gravitational fingerprints it leaves on distant objects have some astronomers convinced it's only a matter of time before we spot it. But not everyone is sold on the rogue planet theory. Some suggest alternative scenarios, perhaps the Kuiper belt's edge marks where primordial conditions in the early solar system prevented objects from forming. Others propose that gravitational tugs from passing stars long ago stripped away the outer debris, leaving behind this ghostly border. There's even a wilder idea that the Kuiper cliff is evidence of an ancient catastrophic event, like a collision that shattered a once larger dwarf planet, scattering its remains. Observations from telescopes like Hubble and future missions like the Vera Rubin Observatory might finally crack this mystery. If Planet 9 is real, its discovery would rewrite our understanding of the solar system's architecture. If not, then the Kuiper cliff forces us to rethink how planetary systems evolve, and what unseen forces might still be shaping ours from the shadows. Whatever the answer, this icy frontier reminds us that even in our own cosmic backyard, there are puzzles waiting to be solved. Up next, we'll turn our attention to Mars, where a different kind of enigma lingers in the thin Martian air, the mysterious methane spikes that could hint at something extraordinary. Now, let's shift our gaze from the icy fringes of the solar system to the rusty plains of Mars, where a tantalizing mystery lingers in the thin Martian air. Methane, a gas that on Earth is often tied to life, has been sporadically detected in the Martian atmosphere, sparking debates that cut to the heart of one of humanity's oldest questions: are we alone in the universe? What makes methane so intriguing? On Earth, the vast majority of methane is produced by living organisms, from microbes to cows. But it can also be generated by geological processes like serpentinization, where water reacts with certain rocks. On Mars, where the atmosphere is a mere 1% as thick as Earth's, methane shouldn't stick around for long. Solar radiation breaks it down within a few hundred years, so when our rovers and orbiters detect sudden methane spikes, it implies something is actively producing it. The first whiffs of Martian methane came in 2004, courtesy of the European Space Agency's Mars Express orbiter. Then, in 2013, a Curiosity rover detected a tenfold spike in methane levels right above its landing site in Gale Crater. These bursts were fleeting, lasting only weeks or even days before vanishing. But why the irregularity? If the source were steady, like volcanic activity, we'd expect a more consistent presence. Instead, these erratic spikes suggest localized, possibly seasonal releases, adding another layer to the puzzle. One leading theory points to subsurface reservoirs. Mars has vast deposits of water ice, and if liquid water exists deep underground, it could interact with olivine-rich rocks to produce methane through serpentinization. Alternatively, methane might be trapped in icy cages called clathrates, releasing bursts when temperatures shift or the ground fractures. Then there's the elephant in the room: biology. While no definitive evidence of Martian life exists, methane spikes align with what we'd expect if microbial life, perhaps extremophiles like Earth's deep-sea methanogens, were eking out an existence beneath the surface. It's a thrilling possibility, but scientists caution that abiotic processes can't be ruled out. After all, Mars has active geology with traces of ancient volcanism and even potential mud volcanoes. To complicate matters, some observations contradict each other. While Curiosity sniffed methane at ground level, the European Trace Gas Orbiter, designed specifically to study atmospheric gases, found barely a trace in the broader atmosphere. This mismatch could mean methane is being destroyed near the surface faster than expected, or that the sources are hyper-localized, escaping broader detection. Future missions like NASA Mars Life Explorer aim to drill deeper and analyze samples with tools sensitive to organic molecules. If they uncover isotopic signatures unique to biological processes, it could be a game changer. For now, the Mars methane mystery remains unresolved, a whisper in the wind that keeps us looking closer, wondering if the red planet holds secrets far more profound than we've dared to imagine. Next, we'll journey to Venus, where another atmospheric oddity swirls at the planet's south pole. A vortex so peculiar it seems almost otherworldly. Now, let's leave the dusty mysteries of Mars behind and turn our attention to Venus, a planet shrouded in thick, swirling clouds. Here, at its south pole, lies one of the most bizarre atmospheric features in the solar system, a double-eyed vortex that defies simple explanation. Unlike anything else we've observed on other planets, this swirling tempest has puzzled scientists since its discovery, raising questions about the chaotic dynamics of Venus's atmosphere. First spotted by the European Space Agency's Venus Express orbiter in 2006, this vortex isn't just a single storm, it's a pair of intertwined whirlwinds, each with its own distinct eye. Imagine two hurricanes dancing around each other, locked in an endless waltz, yet never merging. What makes this even stranger is that Venus has no oceans or landforms to disrupt its atmosphere like Earth's hurricanes do. So why does this vortex split into two? The answer might lie in Venus's superrotation, a phenomenon where its atmosphere spins up to 60 times faster than the planet itself. This creates wind speeds of over 200 miles per hour, whipping around the planet in just 4 Earth days. At the poles, these rushing winds collide and spiral downward, forming vortices. But the double eye structure, that's where things get weird. One theory suggests it's due to atmospheric waves, similar to the way ripples in a pond can create overlapping patterns. On Venus, these waves might interfere with each other, splitting the vortex into two distinct centers. Another idea points to the planet's extreme conditions: surface temperatures hot enough to melt lead and an atmosphere choked with sulfuric acid. These factors could create unstable layers in the atmosphere, forcing the vortex to divide as it struggles to maintain balance. What's even more fascinating is how this vortex changes over time. Observations show it can shift shape dramatically, sometimes appearing as an elongated figure 8, other times as two separate, wobbling circles. This unpredictability hints at a system far more complex than the relatively stable polar vortices on Earth or Saturn. The mystery deepens when we compare it to Venus's North Pole, which also hosts a vortex but a single one. Why the asymmetry? Some scientists speculate it's due to differences in how solar heating interacts with Venus's thick cloud layers at each pole. Others wonder if undiscovered topography beneath the clouds, like massive mountains or ancient lava flows, could be influencing the vortices in ways we don't yet understand. Future missions like NASA Da Vinci and Veritas or ESA Envision aim to peer through Venus's opaque atmosphere with advanced radar and infrared sensors. These could reveal whether the vortex's roots stretch deep into the planet's interior or if it's purely an atmospheric quirk. For now, the Venusian vortex remains a mesmerizing enigma, a reminder that even in our own cosmic backyard, nature has a flair for the unexpected. Up next, we'll delve into the strange world of neutrinos, ghostly particles that seem to defy the laws of physics as they flit through the universe. Now, shifting our gaze from the swirling storms of Venus, let's venture into the subatomic realm, where tiny, elusive particles called neutrinos are rewriting the rules of physics. These ghostly particles, so light they were once thought to be massless, pass through matter almost as if it weren't there. Trillions stream through your body every second without a trace. Yet despite their near invisibility, neutrinos hold monumental secrets, particularly in how they defy the standard model, our best blueprint for understanding particle physics. At the heart of the mystery is neutrino oscillation, the bizarre ability of these particles to change flavors as they travel. Think of it like a chameleon shifting colors mid-journey. Neutrinos come in three types: electron, muon, and tau. But unlike other particles, they don't stay put. An electron neutrino emitted by the Sun might arrive at Earth as a muon or tau neutrino. This shape-shifting implies something revolutionary. Neutrinos must have mass, however slight. The problem: the standard model originally assumed they were massless. Their tiny but measurable masses, confirmed by experiments like Super Kamiok and SNO, force physicists to rethink fundamental laws. Why does this matter? Because the standard model has been spectacularly successful, predicting everything from the Higgs boson to quantum behaviors, but neutrinos expose its cracks. Their masses are far lighter than other particles, suggesting they might arise from mechanisms outside the model, like the seesaw mechanism, where hypothetical heavy neutrinos balance the scales. Even stranger, neutrinos could be their own antiparticles, a property that might explain why the universe has more matter than antimatter. Then there's the anomaly that's really stirring the pot: discrepancies in neutrino data. Experiments detect fewer electron neutrinos from the Sun than expected, and muon neutrinos from accelerators vanish en route to detectors. Some results, like those from the mini-Buani experiment, hint at a potential fourth neutrino, a sterile neutrino that interacts only via gravity. If real, this would upend physics entirely, pointing to dimensions or forces beyond our current grasp. The implications stretch from the cosmos to the quantum. Neutrinos from supernova like SN 1987A arrive earlier than light in certain detectors, not because they're faster, but because they take a straighter path through curved spacetime. Their oscillations could even reveal hidden properties of spacetime itself. Future projects like Dune and Hyper Kamiok aim to crack these puzzles by studying neutrinos with unprecedented precision. So while neutrinos might be the universe's faintest whispers, their anomalies roar with questions. What gives them mass? Are they cosmic keys to dark matter or extra dimensions? For now, these tiny phantoms remain one of physics' most tantalizing loose ends, proof that even the smallest particles can hold the biggest mysteries. Next, we'll turn our attention to a cosmic structure so bizarre, it seems to bend the rules of the universe itself: the Hercules Corona Borealis Great Wall. Now, as we journey from the enigmatic realm of neutrinos to the depths of space, let's marvel at one of the cosmos' most striking visual oddities: the Red Rectangle Nebula. Nestled in the constellation Monoceros, this celestial gem isn't your typical nebula. Instead of the usual swirling clouds of gas, it presents an almost perfect geometric shape, a glowing red rectangle with a lattice-like structure, as if crafted by some cosmic architect. At its heart lies HD 44179, a dying star in the final stages of its life, shedding its outer layers to form this breathtaking spectacle. But what makes this nebula defy the usual chaotic beauty of stellar death? The answer might lie in its hidden companion. Many astronomers believe the red rectangle's stark symmetry points to a binary star system where two stars orbit each other in a tight dance. As the primary star expels material, the gravitational tug of its partner could be sculpting those ejections into precise, geometric patterns like a spinning top guiding the flow of sand. Another clue comes from the nebula's bizarre composition. Unlike most nebulae which glow from ionized gases, the red rectangle's crimson hue comes from a rare form of carbon-rich molecules called polycyclic aromatic hydrocarbons, or PAH. These complex organic compounds, often found in soot or engine exhaust on Earth, thrive in the dense dust disk surrounding the central stars. When ultraviolet light from the stars hits these molecules, they fluoresce, painting the nebula in its signature red glow. But the mystery deepens with its iconic ladder rungs, the series of evenly spaced horizontal bars that give the nebula its rectangular appearance. Some theories suggest these could be shock waves from periodic outbursts of the dying star, freezing dust into precise layers. Others propose they're the shadows of dense dust rings, cast like a starburst by the binary system's orbital motion. The red rectangle isn't just a cosmic curiosity, it's a preview of our own sun's fate. In about 5 billion years, our star too will shed its outer layers, potentially creating a similar planetary nebula. By studying HD 44179, scientists hope to unravel how binary interactions shape these stellar farewells and whether our solar system's end might hold symmetries as striking as this crimson enigma. Yet for all we've learned, questions linger. Why is the geometry so precise? Could the nebula's dust disks harbor the building blocks of life, given their organic, rich content? As telescopes like the James Webb probe its chemistry in infrared, the red rectangle remains a testament to the universe's flair for artistry, where even death can be breathtakingly orderly. Next, we'll unravel the staggering scale of a cosmic structure so vast, it defies the very limits of what we thought possible, the Hercules Corona Borealis Great Wall. Shifting our gaze from the geometric marvel of the red rectangle nebula, we encounter a cosmic structure so immense it challenges our very understanding of the universe's architecture, the Hercules Corona Borealis Great Wall. Picture this, a sprawling tapestry of galaxies, stretching an almost unimaginable 10 billion light-years across, making it one of the largest known structures in existence. To put that into perspective, if you could travel at the speed of light, it would take you longer to cross this wall than the current age of our entire universe. This colossal filament of galaxies, discovered in 2013 by mapping gamma-ray bursts, defies a fundamental principle in cosmology called the cosmological principle. This principle suggests that, on large enough scales, the universe should appear relatively uniform, with matter distributed evenly. But the Hercules Corona Borealis Great Wall shatters that expectation. Its sheer size, roughly 1/10 the diameter of the observable universe, implies a level of clustering that shouldn't exist under our current models. How did such a massive structure form, and why does it stand alone in its scale? One leading theory points to the early universe, where tiny fluctuations in density after the Big Bang may have seeded these gargantuan formations. Over billions of years, gravity amplified those fluctuations, pulling galaxies into the vast web-like structures we see today. But even this explanation struggles to account for the wall's staggering dimensions. Some scientists propose that it might not be a single structure at all, but a chance alignment of multiple galaxy clusters along our line of sight. Others speculate that unknown forces, like exotic dark energy interactions, could have played a role in its formation. What makes this wall even more puzzling is how we detected it in the first place. Because it's so distant, lying about 10 billion light-years away, traditional telescopes can't resolve its individual galaxies. Instead, astronomers relied on gamma-ray bursts, the violent explosions of massive stars, as cosmic beacons. These bursts are so energetic they can be seen across the universe, and their distribution revealed the wall's outline. Yet this method raises its own questions. Are we seeing a true physical structure, or just a temporary clustering of these explosive events? The Hercules Corona Borealis Great Wall isn't just a curiosity, it's a potential crisis for cosmology. If structures like this are more common than we thought, our models of the universe's evolution may need a radical overhaul. It forces us to ask, is the cosmological principle incomplete? Could there be even larger structures waiting to be discovered, pushing the boundaries of what we consider possible? As we ponder these questions, our next stop takes us from the unimaginably vast to the intriguingly dense, a planet where the very ground beneath your feet might glitter like a jewel. Now, from the vast cosmic tapestry of the Hercules Corona Borealis Great Wall, let's zoom into something far smaller but no less extraordinary, a world where the very ground might be made of diamonds. Meet 55 Cancri E, a planet so bizarre it's been nicknamed the Diamond Planet. Imagine a world twice the size of Earth, orbiting so close to its star that a single year lasts just 18 hours, and where temperatures soar high enough to melt iron. But the real surprise, beneath its scorching surface, this planet could be packed with carbon in its purest, most dazzling form. 55 Cancri E belongs to a special class of planets called super-Earth rocky worlds, larger than ours but smaller than gas giants. What sets this one apart is its composition. Most Earth-like planets are rich in oxygen and silicon, but 55 Cancri E is dominated by carbon. Under the extreme pressures and temperatures in its interior, that carbon could crystallize into diamond, creating a core that might literally glitter. Scientists estimate that up to a third of the planet's mass could be diamond, making it worth quadrillions by Earth standards if anyone could actually mine it. But don't pack your space helmet just yet. The surface of 55 Cancri E is anything but hospitable. With daytime temperatures reaching nearly 4,000 degrees Fahrenheit, the planet is likely covered in a molten lava ocean with no solid land to stand on. Its atmosphere, if it has one, would be a toxic mix of hydrogen, helium, and carbon compounds like methane, hardly the stuff of breathable air. Even more intriguing, some models suggest the planet might be tidally locked, meaning one side permanently faces its star, creating a blistering day side and a slightly cooler but still deadly night side. The discovery of 55 Cancri E challenges our understanding of planet formation. Typically, planets orbiting carbon-rich stars are gas giants like Jupiter. So how did a rocky, diamond-packed world emerge? One theory suggests it might have started as a gas giant, only to have its atmosphere stripped away by the intense radiation from its star, leaving behind a dense, carbon-rich core. Another possibility is that it formed in a part of its system where carbon was far more abundant than oxygen, creating a fundamentally different kind of planet from those in our solar system. Studying 55 Cancri E isn't just about marveling at cosmic bling. It's a window into the incredible diversity of planets out there. If a world like this can exist, what other strange, unimaginable worlds might be waiting to be discovered? As we continue our journey through the universe's greatest mysteries, our next stop takes us from the scorching surface of a diamond planet to something even more enigmatic, an object lurking in our own solar system that has sparked endless debate and speculation. Now, shifting our gaze from distant diamond planets to an enigma much closer to home, let's unravel the mystery of the so-called Black Knight satellite. This infamous object has sparked wild theories, from ancient alien technology to a long-lost human spacecraft. But what's the truth behind the legends? First, let's rewind to the late 1950s, when newspapers and radio shows began buzzing about an unidentified object orbiting Earth. Some claimed it was a relic from an advanced civilization, possibly thousands of years old, silently watching us from space. The stories grew even wilder when amateur radio operators reported strange signals, supposedly intercepted from the satellite. But here's the reality check. The Black Knight is far more mundane than the myths suggest. Modern analysis points to two likely explanations. The first is space debris, specifically a thermal blanket lost during a 1965 spacewalk from the Gemini 4 mission. Photos of the blanket floating away match the descriptions of the Black Knight's irregular shape. The second possibility, a misinterpretation of early satellite tracking data. In 1954, the United States Air Force detected unusual radar echoes, which were later attributed to a combination of equipment malfunctions and natural phenomena like meteors. Over time, these fragments of information merged into the Black Knight legend. So why does the myth persist? Part of it stems from our fascination with the unknown. The idea of an ancient satellite taps into deeper questions about humanity's place in the cosmos. Could an extraterrestrial civilization have left a calling card in orbit? It's a thrilling thought, but science favors simpler answers. That said, the Black Knight's legend serves as a reminder of how easily mysteries can capture our imagination, even when the truth is less sensational. What's next in our journey through cosmic enigmas? From the shadows of conspiracy theories, we turn to a controversial technology that seemed to defy the laws of physics itself, the M-drive. Did scientists really stumble upon a revolutionary propulsion system, or was it all an illusion? The answer might surprise you. Now, let's dive into one of the most tantalizing and controversial ideas in modern aerospace, the M-drive. This so-called impossible engine promised to revolutionize space travel by generating thrust without propellant, seemingly defying Newton's third law of motion. For years, it captivated scientists and dreamers alike, offering the glimmer of a future where spacecraft could zip across the solar system without bulky fuel tanks. But how did this audacious idea emerge, and why did it ultimately crumble under scrutiny? The story begins in the early 2000s when British engineer Roger Scheuer proposed a radical concept, a microwave thruster that could create thrust by bouncing microwaves inside a closed, tapered cavity. According to Scheuer, the shape of the cavity would produce uneven radiation pressure, generating a tiny but measurable force in one direction. If true, it would mean propulsion without expelling mass, a direct violation of Newton's principle that every action has an equal and opposite reaction. At first, the scientific community dismissed the idea as nonsense, but then something unexpected happened. In 2016, a team at NASA Eagleworks lab reported detecting a small amount of thrust in their own M-drive experiments. Suddenly, the impossible seemed plausible. Headlines blared about a breakthrough that could shrink travel times to Mars from months to weeks. Enthusiasts imagined interstellar probes powered by this mystical technology. But as with all extraordinary claims, the burden of proof was heavy. Skeptics pointed to a glaring issue. The measured thrust was so minuscule that it could easily be explained by experimental errors or unaccounted for forces like thermal expansion or magnetic interference. To settle the debate, rigorous independent tests were conducted. In 2021, a team at the University of Dresden put the M-drive through its paces in a high-precision vacuum chamber. Their conclusion: the observed thrust vanished when they accounted for external factors. The miracle engine was likely just measuring the subtle push of heat or electromagnetic interactions. So why did the M-drive capture so much attention? Part of its allure lies in the human desire for breakthroughs that bend the rules. The idea of a fuel-free engine taps into our collective yearning for a cleaner, faster future in space. But science demands reproducibility, and the M-drive simply couldn't deliver under strict conditions. While it's a reminder that even flawed ideas can inspire progress, it also underscores the importance of skepticism in the face of seemingly impossible claims. Next, we turn to another radical concept, one that flips the script on black holes entirely. What if instead of devouring everything, some regions of space-time might actually spit matter back out? Enter the enigmatic white hole hypothesis. Now, let's venture into one of the most mind-bending ideas in theoretical physics, the white hole hypothesis. Imagine a black hole in reverse. Instead of sucking everything in, a white hole would violently eject matter and energy, spitting it out into the universe like a cosmic fountain. This bizarre concept emerges straight from the math of Einstein's general relativity, where the equations allow for the existence of such objects even if we've never seen one. So what exactly is a white hole? Think of it as the opposite twin of a black hole. While a black hole's gravity is so strong that nothing, not even light, can escape its pull, a white hole would repel everything. Nothing could enter it, instead it would only expel. Some physicists speculate that white holes could be the other end of a black hole, connected by a theoretical tunnel in space-time known as a wormhole. If that's true, then matter falling into a black hole might be hurled out through a white hole somewhere else in the universe, or even in another universe entirely. But here's the catch: white holes are purely theoretical. Unlike black holes, which we've now observed directly, no confirmed white hole has ever been detected. One reason is that they're thought to be incredibly unstable. According to calculations, a white hole would almost immediately collapse under its own physics, potentially turning into a black hole within moments of forming. So even if they did exist, they might blink out of existence before we could ever spot them. That hasn't stopped scientists from looking, though. Some have proposed that certain unexplained cosmic explosions, like gamma-ray bursts, could be signs of white holes erupting. Others suggest that the Big Bang itself might have been a white hole event, a singularity violently spewing out the material that became our universe. While these ideas remain speculative, they push the boundaries of our understanding and challenge us to rethink how space-time works. The white hole hypothesis isn't just a wild thought experiment. It forces us to grapple with fundamental questions about the nature of reality. If white holes exist, do they hint at a deeper symmetry in the cosmos? Could they be part of a larger cycle of universes being born and reborn? For now, these questions linger unanswered, keeping the white hole one of the most tantalizing and elusive enigmas in our cosmic repertoire. As we wrap up our journey through these 30 cosmic mysteries, one thing becomes clear: the universe is far stranger and more wondrous than we can imagine. And so, as we come to the end of our cosmic journey, let's take a moment to reflect on the staggering mysteries we've explored together. From the invisible grip of dark matter to the explosive possibility of white holes, the universe has shown us time and again that it thrives on the unknown. Each of these 30 phenomena, whether it's the eerie silence of the Fermi Paradox, the puzzling dimming of Tabby's star, or the vast emptiness of the Boötes void, challenges our understanding and pushes science to its limits. They remind us that curiosity is our greatest tool, and every unanswered question is an invitation to dig deeper. Think about it: the more we uncover, the more we realize how much is still out there waiting to be discovered. These cosmic riddles aren't just gaps in our knowledge, they're doorways to new physics, new philosophies, and perhaps even new realities. The fact that we don't have all the answers yet isn't a failure. It's a testament to how wondrously complex the cosmos truly is. And that's what makes astronomy so thrilling. Every observation, every theory, every aha moment brings us closer to unraveling the universe's grandest secrets, or stumbling upon even bigger mysteries. Now, we'd love to hear from you. Which of these cosmic enigmas captured your imagination the most? Was it the haunting beauty of the Red Rectangle Nebula, the relentless pull of the Great Attractor, or the spine-tingling mystery of the WOW signal? Drop your favorites in the comments below. We're excited to geek out with you over these mind-bending topics. And if you're hungry for more cosmic deep dives, don't forget to hit that subscribe button and ring the notification bell. There's always another mystery lurking just beyond the edge of our understanding, and we can't wait to explore it with you next time. Until then, keep looking up. The universe is far from done surprising us.